Good day, folks. Here's the graph of the hot air balloon and the graph of the object that is dropped on a hot air balloon. Now, guys, the first thing that we need to look at here, it says a hot air balloon is rising vertically at constant velocity. That's very important. So it moves at constant velocity. We know what's happening. The acceleration is what? Is zero, right? And when the hot air balloon reaches point A, few meters above the ground, a man in a hot air balloon drops a ball which hits the ground and bounce. Ignore the effect. Let's just draw that. Let's say here's the hot air balloon. It's above this height. It's above this height. When it's at this height, the hot air balloon, it drops an object. It's very important, guys, to understand that the hot air balloon is not on a free fall, not free fall, because there are two forces that are acting on the hot air balloon. It's not the gravitational force only, it's a force of fire, or we can call it's a force that propels the hot air balloon upwards. So two forces that are acting there. So it's not under the influence of gravitational force only, it's not a free fall. Now, a hot air balloon, it moves at a constant velocity and it's ascending. It's rising vertically. So, the object that is dropped when a hot air balloon moves, its initial velocity will be zero. So, let's say here's an object. The object will take that route there. Since it's moving at constant velocity, so the initial velocity here, it will be the velocity of the hot air balloon. So when it gets to the ground and then it bounces the object, when it gets to the ground like that. So where do we see that? Let's finish the statement. The velocity time graph below represents the motion of the ball the instant it's dropped until it bounces for the first time. The interval between the bounces is ignored, which is the contact time is ignored. Upward direction is taken as positive. So even the graph tells us that without being told. Use the information on the graph to answer the following question. Guys, as I've mentioned, the initial velocity of an object that is dropped in a hot air balloon, it's the velocity of the hot air balloon. So this graph, we are shown the velocity of that object that is dropped. So its initial velocity is what? Is zero. So as it moves up, its velocity decreases to what? To zero. In the graph, it's that decreases to the maximum point, and it took 0.6 seconds from there to there. And then it increases further down in the negative direction, you see, up until the ground. So it reaches the ground with a velocity of what? 19.6 in the negative direction. So that velocity will be positive. And then it bounces there. This is a bounce. And it bounced there. And it moved up with a velocity of what? 2,94. That 2,94 decreases to the max, which is there, is it? It decreases to the maximum point at P. This is point P there. There it's point P, and then increases in the negative direction. There is it. It increases in the negative direction. So the whole journey of this object, it took 3.2 seconds. 3.2 seconds. I hope that makes sense, guys. Now let's answer the question. Write down the magnitude of velocity of the hot air balloon. Guys, this graph, remember, it's a graph of an object that is dropped. Remember, I said the initial velocity of an object that is dropped in the hot air balloon is the velocity of the hot air balloon. So the answer here, it's going to be what? 5,88 meter per second. The velocity of the hot air balloon is 5,88 meter per second, and it's moving at constant velocity upwards, right? So question 3.2, it says calculate the height above the ground from which the ball it was dropped. So calculating that, the height in which it was dropped. So we wanted this height, guys, this height in which it was dropped here at this height, right? It was dropped at this height. We want this height. It's the same as that one, guys, but um, let's just put it there to make things clear. It was dropped there. That's the height. The height of the height of in which it was dropped. So we want that height, guys. So wanting that height, this simply means that the motion of a ball from there to there, it's going to be its displacement from there to there, returning where it was dropped, is going to be zero. So starting from there down, it's going to be the height in which it was dropped. So we can calculate using that. So what do we have? So the entire journey from there till the ground, it took 2.6 seconds. So what we can do from that, we can say it's 3.2. What do we have? We have an initial velocity of an object, it's 5.88 meters per second, and the final velocity we do have when it reaches the ground there. Guys, remember, from graphically it's thrown and it reaches the maximum point and then it goes straight to the ground. So this is the final velocity, it's negative 19.6 meter per second. Our acceleration here, remember, we chose what? Upward as positive. So our acceleration, even if you look at the slope of the graph, it's negative. So our acceleration there, it's negative 9.8 meters per second. So we want what? We wanted the height, which is the displacement. So the formula that we're going to use there, amongst the formulas, guys, it's based on what we have. So we're going to use that formula that says vf squared is equal to v initial squared plus 2a change in y. So what is our final velocity? It's negative 19.6 square equal to the initial velocity, it's 5.88, which is positive square, plus 2a. The acceleration is negative. Don't forget that we want the displacement. We wanted the height. Where was the hot air balloon? Where it was thrown. So this will go to this side. We'll have negative 9.6, 5.88 square. We'll have 19.6 and it's negative delta y, and then we divide by negative 19.6 both sides, negative 19.6, and then our displacement there, clearly it will be, since it's going down, clearly it will be a negative answer. So it's 17.84. When you punch that in the calculator, it's negative 17.84 meters. So the negative 17.84, it's when it was dropped, it's this height. So it's this displacement from there to there. It's the same as the height. Guys, let me show you another alternative way to calculate that. Okay, before I do that, I will use the area, guys, without the equation of motion. Guys, I'll have to use this part, which is this part of the graph from the maximum point to the ground. It's this is the maximum point to the ground. So I'll use the area of this triangle and minus the area of from there to there, which is it's where it was dropped till there. So we have two areas, guys, here. We have this area, which is it's from there to there, and then we have which color I'm going to use. Let me use green. From there to the ground, it's this area. So the area, guys, if you check my previous video, the area under this curve, it tells us that those displacement. So I'll say this one minus this one, it will give us the height there. So without using the equation of motion, that's how you do that. So we'll say the height of what? Of the hot air balloon is equal to the area of a triangle, which is the big one, minus the area of a smaller triangle. So it's half base times perpendicular height minus half base times perpendicular height. So the base, what is our base there in the big triangle? The base in the big triangle, it's there. So we're going to say it's the time there, but the time it starts from 0.6 to 2.6. So it's going to be 2, but how do we get the 2? So it's going to be 2.6 minus 0.6, that makes 2. And the height, what is the height? The height is from there to there in this triangle. So this is our height. The height, it's 19.6. Remember guys, we're not going to put the negative there because we already have the negative there. So minus half our base in the small triangle. Our base is 0.6 and our height is 5.88. 0.6 times 5.88. So the answer there, it will be the same as that one is going to be 17.84 meters. So here guys, I was supposed to state the height, it was 17.84. Shouldn't leave it as positive, as negative. The height is not negative. Okay. 3.3, it says calculate the time at point P indicated in the graph. So the point P, it's here. We want this time from there to there, right? But at this time, guys, if you look at it, it's between the two. So we can get the difference from there to there. What is it? Between 2.6 and 3.2. What I'm going to do, I'll say this minus this, divide by 2. It will give me the difference from there to there, and then I'll add it. So this is 3.3, I guess. 3.3, yeah. The time P. So what is it in the graph? I'll say 3.2 minus 2.6. 3.2 minus 2.6. Since it's in the middle, guys, there, I'll divide by 2. So it will give me the difference there, from the difference between in the midpoint, at the midpoint of those. So I say 3.2 divided by 2 is going to be, and then, and another thing that is important there, I have to add. So it will just give me the number from there to there. So, and I have to say plus 2.6 so that I can get in exactly. Okay, let me punch this in the calculator so that I can show you. So it's 3.2 minus 2.6. 2.6, it's 0.6, right? Let me show you the 0.6. The 0.6, guys, it's from, to get this answer here, you add the 0.6 from 2.6 and then you have the answer here, right? So if you add the 0.6 there, if you add the 0.6 there in 2.6, the answer there, it will be 2.9. Right, am I right? So I said 3.2 minus 2.6, and then, yeah. So if I add there, did I divide by 2? No, I did not. I divide by 2. It's going to be 1.9. So it's not 0.6, guys. It's 3.2 minus 2.6 and divide by 2. It's 0.3. So this is wrong, guys. It's 0.3. So it's 0.3. So what I was saying, from here to here, you add 0.3. So if we want P now, we'll say 2.6 plus 0.3, it will give us 2.9. And then that means P, it's what? It's 2.9. Now from 2.9 to to 3.2, you must add what? 0.3. That makes sense now. Okay, now let's look at 3.4. 3.4, it says calculate the maximum height ball reaches. Okay guys, let me show you another way to do this, the alternative way to do this. Guys, another way to do this, let me erase that. So we want the time there, but what is important there, you have the velocity there and the velocity there. This will be the initial and this will be the final. So this is the maximum point, which is at this point, right? From here, this is from here to here. So we wanted the time it took from here to here, right? From here to here. So what are we going to do? We're going to use this and this to get the time there. So we're going to use that formula. We have initial there, it's 2,94, it's positive 2,94, it's positive meter per second, and the final velocity, it's at maximum at 0, and we want the time, and the displacement we do not have. So which formula are we going to use there? We're going to use a VF, V initial plus AT. V final is 0, V initial is 2.94 positive plus the 9.8 that is negative. Remember, it's very important. Then 2.94, it's negative when I transpose to that side. 9.8 change in T, and then our change in T, let me punch that in the calculator. 2.9 divided by 9.8, it's 0.3. So the 0.3 is the one that we got there. So the 0.3, in order to want time P at P, so we're going to say 2.6 plus 0.3, it's going to be 2.9 seconds, right? The time from the beginning, from here to here, it's going to be what? 2.9. But to there, we say add another 0.3. I hope that makes sense. Let's look at the second last question. Calculate the maximum height ball reaches after the first bounce. So the ball goes to the maximum height and goes down, so we wanted the maximum height. We wanted the maximum height there. So the maximum height after the first bounce. So the maximum height we can calculate using the area as there as well. The area there. So we'll use the same, and I'll show you different ways to do that. So let's take the black now. It's 3.4. So what do we have? We still have the initial, which is 2.94, 2.94, and 2.94 meters per second, and the final velocity is 0. And the time, now we do have the time that took from the ground to the maximum point after the bounce at 0.3. At 0.3, that's the time that we just calculate, 0.3 seconds. So we'll use the formula that says we wanted the height. So we'll use the formula that says Vf squared is equal to V initial square plus 2a change in y. Why are we using this one? We want this guy. Acceleration we do have, initial and final we do have. So let's substitute. Final velocity is still 0, and the 2.94, it's positive with square, plus the acceleration 2 times 9.8, negative 9.8 change in y. So we take this to this side, so it's going to be negative 2.94 square, and we'll have this side negative 19.6 change in y, and then we divide by 19.6, negative 19.6, and then our change in y there, when we punch that in the calculator, we'll say 2.94 square divided by 19.6, it's 0.45. meters. So this is, what is the 0.45 meters is the height above the ground from here to here. It's 0.4, right? Must keep that in mind. The last question. Okay, let me show you another way. Before that, we'll use the area under this curve, the area here. If we use this area, it tells us the displacement there. It tells us the displacement there. And so what do we have there? We have the base, which is the time at 0.3. Let me use alternative. We have the base. So that's the triangle. So we'll say area is equal to displacement, which is half base times perpendicular height. Our base there is what? It's time. And what is our time? It's 0.3. And what is our height there? The height here, the height, it's from there to there. The base is there to there. So we already put the base there, it's 0.3. The height, it's 2.94. It's 2.94 is half. If I punch that in the calculator, I say half times 0.3 times 2.94, it's 0.45. 0.45 meters. That's how you calculate without using the equation of motion. In this case, it's when they do not want the equation of motion. Okay, the last question, guys, before we end this. Calculate the distance between the ball and the hot air balloon when ball is at maximum height after the first bounce. So when the ball it's at maximum height after the first bounce, this is the first bounce, and then which is the maximum height, it's there. So how long it took to reach the maximum height there? How long it took? So it took this time, right? Because it come from the ground and it decreases its velocity to the maximum height, which is from there to there. So the time it took, it's 2.9. And that's very important. The ball, these are the information for the ball. The time it took, it time of the ball, it's 2.9 seconds to the max height of the first bounce. Now, what do you need to keep in mind when the ball reaches its maximum height? There, it took 2.9 seconds to there. Even the hot air balloon from there to where it is now. Let's say the hot air balloon and now it's here. So the time it took for a hot air balloon from there to there, it's 2.9 as well. So we can calculate the height of the hot air balloon from where it started after 2.9 seconds. So we can say height of hot air balloon, right? So one thing about the hot air balloon, its initial velocity is equal to the final velocity, which is it's moving at constant velocity. So its initial and final is going to be the same, 5.88 meters per second. And the acceleration is 0 because it's moving at constant velocity. And the time it took, it's 2.9 as well. The hot air balloon. So now we're going to calculate where the distance it has covered, the hot air balloon, where it is now. So how do we do that? The distance traveled. Let not say height of the hot air balloon. Let's say it's a distance traveled by the hot air balloon since the ball it was dropped. So it's a distance of the hot air balloon. It makes sense to say distance. Let's say distance of hot air balloon since ball dropped, right? Right? So those are the things that we have there. So we use the formula that says dy is equal to vi change in t plus half at square. So we want that. Guys, exactly what we want here. We want this distance. Since the ball it was dropped, it moved this distance, right? So when it gets there, the ball that was dropped, it's there, right? So when the hot air balloon gets there, the ball it gets to the maximum height, and they have traveled. What is common between the two? It's the time. So the initial velocity of the hot air balloon, it's 5,88, and the time it's 2,9 that it took, and then half the acceleration is 0 and the time it's 2,9. You can just say that side it's 0, and then the answer when you punch that in the calculator, 5,88 times 2,9, it's not just 2, yeah, it's 2,9, it's 2,9. So the answer there, it will be the answer there, it will be, when you punch that in the calculator, it's 17.05 meters. So this is the height here, this height here, where it dropped, it's 17.05 meters, right? So now what are we going to do now? We're going to um, we're going to add the hot air balloon. The hot air balloon now from the ground, if we add that as well, because we have the height of the hot air balloon. So from the ground, the hot air balloon from the ground, so we'll say hot air balloon from the ground, it's both distances. So it's going to be this distance that it travels, 0.45 meters, and as well, what is the height that we calculated, the height of the hot air balloon? So it was 17,84. So if we pass that in the calculator, it will amount to 34,89 meters. What do I mean about this? Why did I add these two? So these two, the 17,84, it was the height, and then now we added this, so it's the height of the hot air balloon from the ground, right? Height of the hot air balloon from the ground. So what are we going to do in order to get the distance between them? Since it's here, since this is here, what are we going to do? We wanted the distance, so we want this part, right? We want this part here. So what are we going to do in order to get that? So from that we'll minus, since we know from the ground it's that. So if we minus this, so it will tell us what is the distance between them. I'm not sure if you get me. So the hot air balloon from the ground, it's that 30 what? 34,89. It's 34,89 from there to there. But now if we can minus that, it will tell us, because the ball it will be there, so we just want the distance, we want this. So if we can subtract this from the entire, we'll have that. So now the final answer, we say distance distance between balloon and ball is, so the distance between them, we subtract, we say 34,89 minus 0.4. What is the 0.4? Is the maximum height that it reached after the first bounce. So the answer here, it will be 34, 34,45 meters. If you punch that in the calculator, basically it's this, it's from here. to here, the distance between them. So we subtracted this, the height we calculated, that 0.45 there. Right, so that's it guys. Have a nice